All right, so welcome back everyone to the fifth lecture in the mini course series. Today, Nat will be talking about partition functors and universal exponential relations.
Yeah, great. Okay, you made it to the end. Um, that's fantastic. So this talk is a little bit different from the others in the sense that it's more of a talk about current research. So this is some ideas that came out of the Kentucky Bourbon Seminar 3 years ago, and I'm currently in the process of writing this up with David Murley and Millie Rose. Uh, but I do want to connect it as much as possible to the previous four lectures. And so I'm gonna start with a different introduction than I used when I gave this talk 3 weeks ago at Newton, in case you saw that. But then a lot of the rest of the talk will probably be similar to that talk at Newton. So I just want to I want to start by thinking about global Mackey functors for a second. So I never gave a precise definition of a global Mackey functor. Um, and uh, and so what is such a thing? Well, um, well, there are several ways to give a definition of a global Mackey functor, but the most compact way to give a definition from scratch is to say that it's a pair of functors, M upper star from groups op to ab, and M lower star from groups and injections to ab. That agree on each finite group and satisfy a double coset formula. And this is almost the definition of a global Mackey functor. There is something wrong here, though, or something incomplete. And that's that we don't actually mean to use the one category of groups when we do this. We actually mean to use a 2-1 category of groups. So really need a 2-1 category of groups. So these M upper stars, the restrictions. I should have said this. M upper stars, the restrictions. M lower stars, the transfers. Hopefully that made sense given the previous four lectures. And what is this 2-1 category of groups? Well, it's group homomorphisms, but then the two isomorphisms are given by conjugation by elements in the target. So if I have a pair of maps from H to G, then a two isomorphism between them is a sigma in G such that sigma F sigma inverse is G. Maybe the conjugation should be the other direction. Whatever makes things work out. And the fact that ab is actually a one category in this definition just means that by taking this to be the 2-1 category groups, we have conjugate maps go to the same map. So conjugate maps between finite groups go to the same map. Or said another way, that action uh, there's um, there are special automorphisms of any finite group, the inner automorphisms, the ones coming from conjugation, and those just all need to go to the identity map on M of G. So that's another way of saying this. So conjugation in the group doesn't do anything on the value of the global Mackey functor on the group. And once I say that, then this really is the definition of a global Mackey functor. This is fine. Um, so that's one thing that I wanted to emphasize that I had not emphasized before. And there's a few other things that I wanted to emphasize from the previous lectures. So we talked about exponential relations in the previous lectures. And for instance, we talked about this one for representation rings, that the sum of the symmetric powers, or m greater than or equal to 0, is exp of the sum over k greater than or equal to 1 of psi k over k, t to the k. And I said very briefly, where does such a thing make sense? And you might think, well, it makes sense in the rationalization of the representation ring of G, double brackets T, and that's true. It does make sense there. But it actually makes sense in a smaller ring, which is more integral, and that's this ring of div like the divided power series ring in one variable over Ru of G. And what the heck is that? So an element in here looks like a sum over I greater than or equal to 0 of R sub I t to the I over I factorial. Um, so that's what you're allowed to, those are the kinds of power series that you're allowed to write in here. And there's also a notion of a divided polynomial algebra in one variable, and then it's just polynomials of this form. And you can do this over rings with torsion too, and then you have to be much more careful about what you mean by t to the I over I factorial. But you can do it. There's a notion of a divided polynomial ring in one variable over a ring that has some torsion in it. Uh, okay. But these are the kinds of things, these are the kinds of things that live in here, and then this power series makes perfect sense in this ring. And so this whole equation can be made sense of in here. So then to move towards what this talk is actually about today. So now let's say I have some global power functor R. So if R is a global power functor, so remember that that's a global green functor. So my global Mackey functor takes values in commutative rings. The restriction maps are ring maps. I have Frobenius reciprocity for the transfer maps. And then there's also power operations from R of G to R of G re sigma M, and these have to satisfy some identities. If R is a global power functor, then I always have this power operation from the value on the trivial group to the value on the symmetric group. We'll call this PM. And because of the way that PM acts on the sum of two elements in R of E, or behaves on the sum of two elements in R of E, if I mod out by that transfer ideal, the transfer ideal which comes from taking transfer maps from sigma I times sigma j to sigma m, um, then then this composite is always guaranteed to be additive. And our goal today is to describe an exponential relation that looks like this. So I take the sum over m greater than or equal to 0 of Pm t to the m, and this is supposed to be x of the sum over k greater than or equal to 1 of pk mod I transfer t to the k. So that's our goal. And in an ideal world, this would in some way specialize in the cases that we care about to give the exponential relations that I've described in our lectures. Um, but if you look at this, it doesn't type check at all. It looks pretty nonsensical. The targets are very different. Um, and also there's this weird fact that we had all these divisions before and there's no division on this side. So like how can this make any sense? And that's the first purpose of this talk. The first thing we're going to get into in this talk is trying to find a home for an exponential relation like this. Okay, so that's what's going on today. Are there any questions? Okay. And so this brings us to a new object in global algebra that I call partition functor. Um, and you should think about these things as being similar to global Mackey functors. So I'm going to replace the 2-1 category of groups with a 2-1 category of partitions. And these are set partitions, not integer partitions. And I'm going to call this category P. And the objects in P are simply, I'm going to denote them with a capital Greek letter like this, and they're simply a choice of a finite set and an equivalence relation on that finite set. So a set partition. And a morphism between two such things. So if I have some other one, omega, which has the equivalence relation twiddle omega on the finite set y, then a map in this category from lambda to omega is a bijection, f from x to y. That respects the equivalence relation. So if x is lambda related to x prime, then f of x is omega related to f of x prime. But I said this is a 2-1 category, so I need to describe the two isomorphisms here. And for that, I need one other additional object associated to a partition, which is a symmetric group associated to the partition. So let's let sigma omega, this is the symmetric group associated to omega, be the group of automorphisms of omega that are the identity when I mod out by the equivalence relation. So they're automorphisms that send each equivalence class to itself.
Oh, P is a partition of something?
P is a category. P is a 2-1 category.
Okay.
So I'm describing this category of partitions.
Uh-huh.
Sorry. There's an S there. That maybe is what's bothering you, that S. A 2-1 category of partitions, which I'm calling P. And the objects are set partitions. The maps are bijections that respect the equivalence relation. And I haven't told you what the two morphisms yet, but they're going to use this sigma
Wait,
omega.
X is not a category.
X is a finite set.
Oh, it's finite set. Okay. I thought it was a finite cat. Okay, cool.
Oh yeah, that is just a terribly drawn S.
Okay, cool. Cool.
Um, so a two morphism between two maps f and g from lambda to omega is simply an element in sigma omega such that sigma f equals g. And and since a sigma like this is a bijection, so since a two morphism is an automorphism of the target, there can be at most 1-2 isomorphism between any two one morphisms. So this category that I'm describing here is equivalent to a 1 category. But I think it's best to think about it this way because it's easier to compare with the category of groups this way. So that's why I'm trying to say it this way. Okay. So it's equivalent to a 1 category. It's also like a graded category, right? Again, because the morphisms in here, the underlying map between sets is a bijection. So it's a graded category. And it's a symmetric monoidal category because if I have two partitions, I can always take the disjoint union of two partitions. and that's some other partition. So let me do some examples, and then we'll see if there are any questions about this category. So let's let M underline be the trivial or indiscrete, also called indiscrete equivalence relation on the set 1 through M. This is the most important partition in this category. And in this case, so this is where all of the elements from 1 through M are related to each other. And in this case, sigma sub underline is just the ordinary symmetric group. Uh, but if I take sigma of I disjoint union J, well, because of the way sigma is defined, there can't be any cross terms here, even if I equals J. And so this is just always sigma I times sigma J. So there's one other thing that I want to say about this category, which is that because there's underlying sets, there's a notion of a subpartition. So I say that lambda is a subpartition of omega written with a less than or equal to if they have the same underlying sets and the identity map is a map of partitions. So this is supposed to be an easy category, but I know that like maybe it takes some processing. So are there any questions? I'm going to explain how it's related to the category of groups in just a second. But first, let me tell you what a partition functor is. So a partition functor M is a pair of functors, M lower star from P to ab and M upper star from P op to ab, satisfying, such that they agree on objects. M star of lambda is M upper star of lambda, and satisfying double coset formula. Involving the symmetric groups associated to the partitions. You don't want me to write it down, but it's some double coset formula just like the one for a global mapping functor. Um, and, and so a natural question is, where do such things come from? And this is the first example, and this is also going to tell us how this relates to the category of groups. So let's
Yeah,
let,
the example we had above with sigma with the I and J, um,
yeah,
um, is uh does I disjoint union of I and J have like a different equivalence, have something different than the trivial equivalence relation on it?
yeah, it's the disjoint union of partitions. So the things are so it's the equivalence relation where all the things in I are related to each other and all the things in J are related to each other, but there's nothing going in between.
Oh,
That's what I disjoint union
also
J means.
the trivial uh the trivial thing is like everybody goes in one cubby.
Everyone's in one equivalence class here. Trivial
Okay.
means trivial underlying topology is the trivial topology. Trivial
Okay.
topology, everything has to be related. That's why I also wrote indiscrete because it's not the discrete one.
Oh,
But
okay.
trivial is the
Satisfying.
right name for this because it's the thing with
Yeah.
the trivial topology underlying it.
Nice. Okay. Cool.
Um, so recall that groups is this 2-1 category of groups, then that we described before. So if I fix a group G, then there are two functors um, from P to the category of groups, and one of them is G wreath sigma blank. And these are functors of two one categories. And the other one is G times sigma blank. And given a global Mackey functor, we can restrict it uh, along either of these to get a partition functor. Partition functors. So given some global Mackey functor, I can fix any group. Are you missing an op somewhere? Right. No, I am not missing an op anywhere. Um, I'm not missing an op anywhere. This op is again because I'm going to think about these M upper stars as restrictions, and I'm going to think about the M lower stars as transfers. But these maps really are covariant functors from P to groups. And what I'm really doing when I say restrict is that I've got M star, M lower star, and M upper star coming out of groups, and I can restrict either of those along this, and that gives me a pair of functors like this. Does that make sense? Or okay, good. So this means that we have lots of examples of partition functors because given any global Mackey functor, I get every object in the global every group determines two partition functors. So there's lots of examples. But even if there's lots of examples, you can say, why are you doing this? And that's always a good question because we feel we feel tortured by new ideas. I certainly do. So the answer is that this category of partition functors admits a very interesting monad that I'm going to call div. I want to describe this monad now. And this monad is like playing the role of integer valued class functions on symmetric groups. That's how to think about what this monad's doing. So let me say what this is. This is going to be the most technical part of what happens going forward. But given what we've done so far, I think it's worth it. So let's let M be a partition functor. Then there's always a notion of a kind of transfer ideal. They're not really ideals because nothing's a ring here, so they're like transfer subgroups. So this is going to be called I sub omega, contained in M of omega, and it's the image over the direct sum of the proper subpartitions of omega of the transfer map from gamma to omega, which I could have just written TR sub gamma omega. Probably that would make the most sense to everyone right now, but also this is notation that we just defined, so I'm using it. And this is a subgroup of M of omega, and we're going to make use of the quotient M of omega mod I omega. Right now, it's just a partition functor. There's no ring structure or anything like this. It's just a subgroup that we have. And I need one other, I need to note one other piece of structure sitting around. So if I have a subpartition omega of lambda, and I have some element in sigma lambda, so that's an automorphism, it's a special automorphism of lambda. Well, then I can apply that automorphism to omega to get a new subpartition, well, potentially new subpartition of lambda called sigma omega. And since sigma sends the proper subpartitions of omega to the proper subpartitions of sigma omega, this induces an automorphism, wrong, an isomorphism from M of omega mod I omega to M of sigma omega mod I sigma omega. So an element in sigma lambda induces an isomorphism like so, just because it sends the proper partitions, the proper subpartitions of omega to the proper subpartitions of sigma omega. And now I can tell you what div is. And it's probably going to look weird the first time you see it. So let's let div of M, I'm trying to construct a monad. So this is supposed to be a new partition functor. So in particular, I'm supposed to be able to tell you what its value is on a partition lambda. This is going to be, well, I'm going to take the direct sum over all subpartitions of lambda. Lambda is a perfectly good subpartition of lambda, of the value of M on omega mod this transfer subgroup I omega. And then there's this sigma lambda action on this entire thing. And I'm going to take the fixed points for the sigma lambda action. So I want the invariance. So the sigma lambda action is sending summons to other summons via isomorphisms. And I want to take the invariance for that. There's a very special summand in div of M of lambda, and that's M of lambda mod I lambda. That's a perfectly good summand in here. And sigma lambda sends M of lambda mod I lambda to itself, but even more, each automorphism in sigma lambda is isomorphic to the identity automorphism. So, so the invariants for the sigma lambda action on M of lambda mod I lambda are everything. So there's a summand in here. This is kind of critical. There's a summand in here, which is M of lambda mod I lambda. So this is coming from the fact that the sigma lambda action on M of lambda is a kind of conjugation action. Okay, it's not really conjugation because we're working with partitions, but if I think about it in terms of groups, it's like a conjugation action. And so just like in the case of a global Mackey functor, that those should be acting by the identity. Okay. So this is some crazy looking thing when you first see it. Um, but this turns out to be a good thing to consider. So it turns out that div of M is another partition functor. And in fact, and div itself is a functor. And it's more than that, it's a monad. And this is something that anybody listening to this could prove. It is just an enormous amount of bookkeeping to check this. But you can do it. You just have to sort of grind out the bookkeeping. But I want to tell you what I want to give you just a rough idea of what the maps are because okay, it's like the div of M is supposed to have restriction maps and transfer maps. So what are those? So the restriction map, so if I have some theta less than or equal to lambda, the restriction map is just a projection. I can just project onto the summons that are the omegas contained in theta. And so that's where the restriction maps come from in the partition functor div of M. The transfer maps, if theta is contained in lambda, the transfer map from div of M of theta to div of M of lambda is a kind of double coset formula. So it really looks a lot like the double coset formula we saw on class functions. Um, so so you can think about it. You can think about it as like inspired by the transfer map between class functions of H to class functions of G when H is a subgroup of G. It's that kind of a formula. The most important one for the purposes of the talk today is the unit map for the monad structure. This one is worth notating. So the unit map for the monad structure goes from m of lambda to div of m of lambda. And so how do I get from m of lambda to this thing? Well, this is a sum. And so for each summand, I want to map from m of lambda to m of omega mod I omega, and there's a natural thing to do. I can restrict to omega and then quotient by I omega. And that's how I get a map from m of lambda to each summand. So I restrict to omega and then I quotient by I omega. And that's the most important map for the purposes of today. But there is also the multiplication for the monad structure. And the multiplication for the monad structure, that's going from div of m back down to div of m. And it uses the fact that I've got these special summons sitting inside of here. So it's not actually a projection onto these summons, but it's sort of induced by the projection onto these summons. So that's how we get from div of div m back to div of m.
And I was wondering, would you want to scroll up a little bit? I'm just trying to remember what M is.
M is a partition functor.
Okay, cool, thanks.
Okay, any other questions? So since the category of partitions is symmetric monoidal, as we can take the disjoint union of partitions, there's a lot of multiplicative structures you could try to put on a partition functor. So you could talk about lax symmetric monoidal partition functors. You could talk about symmetric monoidal partition functors. There's a notion of a partition ring. So a partition ring takes values in commutative rings, and the restriction maps are ring maps, and the transfer maps satisfy Frobenius reciprocity. So there's all these kinds of multiplicative structures that you can put on these things. I'll just write many multiplicative structures. And if I have a partition green functor, sorry, if I have a global green functor, and I restrict it along either of these functors right here, I get a partition ring. So this is one of the properties that these functors have. Basically, any structure that I have on a global Mackey, any multiplicative structure I have on a global Mackey functor, when I restrict it, I get some kind of multiplicative structure on the resulting partition functor. So if I have a global green functor, I restrict it, I get a partition ring, which I could have called partition green functors, but like, yeah, I don't know. I think partition ring is a better name for this. Um, The most important multiplicative structure for us today is the notion of a partition power functor, which is what you get when you restrict a global power functor to be a partition functor. So what the heck is this? So a partition power functor is a partition ring equipped with multiplicative operations, which I'll call P sub m, going from the value, well, let's name this thing R, going from the value on the partition 1 underline to the value of R on partition M underline. And satisfying the exact identities we've been talking about the entire time. But it only has power operations going from R of 1 underline to R of M underline. Okay? So that's the source of a power operation is always R of 1 underline. The identities are the kinds of things that we're used to, right? The value of the power operation on 0 has to be 1. P0, which goes from R of 1 underline to R of 0 underline, has to be the constant function at 1. And then I need to know how it behaves on sums, and it needs to restrict properly to external tensor products of lower power operations. Those kinds of things, the kinds of things we're used to.
In the examples that we studied,
Yeah.
were the power operations determined by what happens at the identity?
Well, it's more that it's the better thing to think about is restricting along either of these. Okay.
Yeah.
So what the way to think about what I'm doing is fixing G, okay? And then I'm only interested in the power operations
Gotcha.
out of
Okay.
the value on G.
Yeah.
And I
Okay.
can
So
either take the power operations that land in the wreath product, or I could take the power operations where I restrict along the diagonal
mhm,
and land in the product.
mhm.
Does that make sense?
Yeah. So you're not claiming that it's determined by what happens at identity, but you're fixing a G.
It's more like, well, if I fix a G, the value of R on one,
Yeah.
if I have some global power functor like RU, and I restrict along G times sigma, then the value of the restricted thing on one is RU of G.
Okay.
And the value of here is RU of G times sigma M. And that's
Gotcha.
exactly the kind of thing where there should be a power
So
operation.
you're redefining R.
Well, R is just some partition ring in this case, but it in the example that I was just referring to, R would be RU of G times sigma blank.
Okay.
Okay?
Okay. I think I'm okay. Thank you.
So the point is that I don't want all the extra stuff in the definition of a global power functor that's hanging around. Instead, I'm interested in the power operations on the value on a particular group. And the data that I need to capture just that information is exactly the notion of a partition power functor. That has just the minimal amount of information to talk about the power operations on a particular group. Okay? Uh, okay. So we have ways like partition rings, we have these partition power functors, and it turns out that div is a monad on all these categories. So div is very well behaved. All of these categories. So the category of partition rings, the category of partition power functors, and so on. I want to do an example. This is important. We are definitely at the stage where examples are required. So let's talk about the initial partition ring. So recall that the Burnside ring is the initial global green functor. So you might think that the initial partition ring is just like the Burnside ring of sigma sub lambda, right? Something like that. That would be a natural guess for what the initial partition ring is. But it turns out to not be correct. So let's let angstrom of lambda contained in A of sigma lambda, this is indicative of the previous things that we talked about, be the subgroup generated by elements of the form isomorphism class of sigma lambda mod sigma gamma for gamma a subpartition of lambda. These are the Young subgroups of sigma lambda, the Young subgroups of sigma lambda. And these Young subgroups are closed, as we've discussed before, they're closed under conjugation and intersection. So this is in fact a ring. This is a subring of A of sigma lambda. And these things assemble into a partition ring. Even a partition power functor. And this turns out to be the initial partition ring. And it's way smaller. It's way smaller than the Burnside ring of sigma lambda, right? The Burnside ring of sigma lambda, I can mod out by any conjugates. I can mod out by any subgroup in sigma lambda. Of course, there's lots of subgroups and symmetric groups. Instead, it's just the Young subgroups that this is supported on. But there's a surprise here. At least I found it surprising. So I'm going to put a question mark. Maybe you'll find it surprising. We can consider the composite of the inclusion of angstrom of lambda into A of sigma lambda, and then linearize to get down to the complex representation ring of sigma lambda. And it turns out that this composite is an isomorphism. So what did we just learn? We just learned that the initial partition ring is the representation ring of the symmetric group partition ring. And we can try and understand what div is doing in this setting. And we've spent time thinking about representation rings. We had 2 lectures. So one thing we learned was that if I take the representation ring of sigma lambda, okay, sigma lambda is just a product of symmetric groups. And if I mod out by the transfer ideal in RU of sigma lambda, this is just Z. So div of RU of sigma blank on the partition M underline, well, the definition is that this is the direct sum over subpartitions of M underline of RU of sigma lambda mod I lambda, but that's Z. And then I take sigma M invariants. But the sigma M invariants are just identifying summons with the same underlying integer partition. So we've got subpartitions of M underline. That's just all set partitions of M. And the sigma lambda invariance is exactly identifying the summons corresponding to subpartitions of M with the same underlying integer partition. So this is isomorphic to the direct sum over the integer partitions of M of Z, otherwise known as the integer value class functions on the symmetric group. And the map eta, which is the unit map for our monad structure, is a map from the representation ring of sigma M, that underline doesn't even need to be there, to div of RU of M, which is integer value class functions. You're not going to be surprised to learn that this is the character map. And so this partition functor business and this div monad has baked into it the fact that representations of symmetric groups have characters that are integer valued. The characters of the representations of symmetric group are integer valued. Okay. So that's this example. I think this is probably the most important example. It explains a real difference between partition functors and global Mackey functors. The initial partition ring is actually the representation ring functor rather than the Burnside ring functor. Okay, I want to get somewhere, and I'm going to succeed. Okay, excellent. 12 minutes, I can do it. So then, are there any questions here? So this next section is called symmetric functions in R, where R is some lax symmetric monoidal partition functor. So given a lax symmetric monoidal partition functor, doesn't even need to be a partition ring, R, we can form the following thing, which I'm going to call R square brackets sigma. This is the direct sum over m greater than or equal to 0 of the value of R on m underline. And this is a commutative graded ring. And where's the ring structure come from? Well, I've got the value of R on I, tensor the value of R on J, and I want to get something in the value of R on M underline, where M is I plus J. And so what I'm going to do is use the lax symmetric monoidal structure, which we think about as an external tensor product. This lands in R of I underline disjoint union J underline. And then I'm going to transfer along I underline disjoint union J underline, landing in I plus J. Underline the whole thing. And this lands in R of I plus J underline. And so that's where my multiplication comes from. And so even though R wasn't ring valued, the lax symmetric monoidal structure puts a ring structure, induces a ring structure on this direct sum right here. And similarly, I can form a power series version of this, R double bracket sigma, which is just where I take the product over m greater than or equal to 0 of the value of R on m underline. And this is a perfectly good commutative ring. It's no longer graded because you need direct sums for things to be graded, but whatever, doesn't matter. And the thing we've been after this entire talk uh, is the following. So the thing we're interested in is the map of commutative rings from R double bracket sigma to div of R double bracket sigma. And a good name for this target is R double angle brackets sigma. And this is supposed to make you think about what we were talking about at the beginning, which is we wanted a home for an exponential relation, and the exponential relations previously required some kind of divided powers to make sense of them. And here is a target that at least I'm notating so that it looks like divided powers. So if R is in fact a partition power functor, then I can take the value of R on 1, and I can take the power operation. This lands here. I can mod out by the transfer ideal, I of m bar, and here I get Pm mod I m bar, which is some additive map, guaranteed to be additive. But R of m bar mod I m bar is a summand of div of R of m bar. And so there's two ways to get from R of m bar to div of R of m bar. One of them is to quotient and then include as this summand. And the other one is to use eta. And this diagram does not commute at all. Here I'm including via this summand. On the other hand, this was restrict and quotient onto each summand. And so I have two ways to start with something. I have two ways to put the mth power operation into div of R of M bar. And this brings us to our first theorem. So let's assume that R is a partition power functor. Then in our double angle brackets sigma, we have an exponential relation between the sum over m greater than or equal to 0 of Pm t to the m. Let me leave some space here. And the sum over k greater than or equal to 1 of pk mod I k t to the k. And I left that space because now we're in a situation where we can sort of we can sort of understand how to parse what's going on here. So this first one is going in to R double bracket sigma via eta. Let me put in some colors. This one's coming in via eta. And if I call this U, this one's coming in via U. So that I don't really want to write those, but you see that now we are in a world where we have enough control over these power operations, and we have this very interesting target where we have multiple ways we can put things in, and we use both of them to get the exponential relation that we want. And this has a nice corollary. So the corollary is that if S is a lax symmetric monoidal div algebra, div is a monad, and we have a map of lax symmetric monoidal partition functors from R to S, then we get for free a factorization through div of R, the free div algebra on R, and thus an exponential relation over S. So I can push the exponential relation here along this map that I got for free to get an exponential relation here. And this, so I was very excited about this when I first understood what was going on. But it turns out that it's not as powerful as you'd like because in practice, it's a little bit, although it's possible to handcraft div algebras, even though I don't really know what a div algebra is, in practice, it's a bit hard to construct maps like this because it just is asking too much of the world for a map to be a map of partition functors. Uh, but you can prove a stronger theorem under stronger hypotheses. So if R is a symmetric monoidal partition ring, and R of M underline mod I M underline is a flat R of 0 module for all M in N, then it turns out that div of R bracket sigma is the divided power envelope of the ring R bracket sigma. And divided power envelope always needs an ideal, and it's the ideal of things in grading greater than 0. there's a canonical ideal in this situation for it to be the divided power envelope with respect to. And now this is just a statement in algebra now. Now I'm just working with commutative graded rings. And this theorem is powerful enough to use the exponential relation that I've described right here to get both Ganter's exponential relation and the symmetric powers for representation ring exponential relation, and also like the exponential relation for exterior powers, all of the exponential relations that people know about involving these things. This theorem is powerful enough to get them all from this one right here. So this is a more universal exponential relation. Okay, I'm going to stop there. I'm done.
All right, let's all thank Nat for the last lecture.